It is the 9th. Cool. Good morning, Nick. How are you? Minutes ago. What a life. Imagine being able to sleep past like 7:30. I even set my alarm for 8 this morning and I woke up at 7:20. Did you seriously wake up a minute ago? That's terrifying. I feel like thinking about topology after being awake for 1 minute sounds very difficult. Yes, but might it be more difficult when half asleep? There are gradations to these things, you know? Nah. Alright then. Can't argue with that. I can picture you saying that. Alright. Okay, so just kind of waiting on Devin. And has anyone heard from Riley recently? Because I didn't get an email response back. Because I know you guys have a group text. I don't know how often you use it, especially now with Discord. Okay. Alrighty. Well, alright, let's go ahead and get started. I think that we're basically all here. So just a little announcement or two first. So reminder that tomorrow night, just get me your outline. Right, it doesn't have to be insanely detailed. I just want you to show me that you've been thinking about this a little bit, have an idea of what you want to write about, and that'll set you up to start the rough draft. And then other thing, which maybe is bigger, is there will be no second exam. We're going to have 2 more problem sets probably instead, and then a final, which is not cumulative. So the final, it'll basically be, our first exam was essentially over the first half of the semester. The final will be over essentially the second half. And obviously, it's cumulative at heart because we're continuing to use all the things we started with, right? We've been using a lot of stuff from chapter 0 lately with the pre-images splitting over unions and whatnot. We've been using definitions of open sets all the time, but there will be no specific questions on those things. I'll be trying to get at the heart of the stuff we've done in the second half. So no second exam, just final over second half material. I just don't think trying to rush that, especially with you guys having a project as well, makes sense. And then I'll kind of just spread out the weight of that towards the other things somewhat equally, I think. I don't know whether to be afraid or happy. That's fair. Yeah, it'll be the same form as the first exam. So maybe ever so slightly longer, but not much, because I don't want it to be too heavy. I would expect it roughly the length of a problem set, which I hope the first exam was roughly. Maybe it was a little bit longer because some of those had parts, but hopefully it was also maybe a little bit easier. Judging by, I don't know. Yeah. those are my thoughts. Feel free to ask questions. About the same, a little easier. Yeah, the goal is a little bit easier because you don't have me, right? So I think making it like a problem set would be tough. Okay. How'd you feel about this problem set? From looking through it, it went about how I expected, or not problem set, but daily homework. I think homeomorphisms, especially from quotient spaces, are hard. So I imagine this felt tough. I hope that today is enlightening. Yeah, all right. I think that's normal. The first time you see these things, actually trying to construct like explicit maps and stuff can be tough. And I had you try 215 on your own first, the homeomorphism from the quotient map, but like I said, look at 217 afterward, and you'll see once we prove that and talk about that life is much, much easier. Yeah, you're not wrong. No, but again, like, that being expected is fine. Like, if you did super well on that the first time you had ever seen that, I mean, I would be crazy impressed. So, like, I say as expected, not just to, like, dull the blow, but also because I'm telling the truth. Like, it's hard. Quotient topologies are weird, and homeomorphisms, like constructing them from spaces that don't necessarily look a lot alike, is a challenging thing to do. All right. On the other hand, I think 209 went pretty well, so let's talk about that. So maybe you guys type in chat some of these. So we kind of just did a list, right? And the open interval stuff, all being homeomorphic, basically gives you the other ones, right? Like the maps are very similar if you want to do half open with half open or closed with closed. So we wanted in pieces, and almost all of these, it should be immediate that these are homeomorphic. We shouldn't really have to prove anything because we have taken calculus. So we had just kind of steps, right? So just kind of write them out. So if you just put like the number like 1 and then some map or something, fishing for insults. It's actually kind of true. I mean, I'm pretty good with insults. I've been told I can be savage. I don't know, Mark, you can probably confirm or deny based upon office hour experience in the past. Big sad. Yeah, so the first one is just f of x equals x plus a. It's just a shift. That's clearly continuous. You also basically prove that with the x plus 2 thing on the last problem set, right? I mean, it's no different for a and 2. Yep, second one is just flip the sign. It's its own inverse. Again, clearly 3, same as 1. I agree. Okay, and yeah, I guess all of these are going left to right. Yeah, so 4 is the first more interesting one. So we get the natural log, and thus, we have the inverse there is e to the x. Both of these are well known to be continuous on their domain, so we're good. 5, you did 2 to the x. You could also do e to the x, yeah, some base greater than 1. So maybe I'll put e to the x or 2 to the x. Sure. The sixth one, a times b over a to the x. I don't think that works. A times b to the a. So this one's interesting. Are you sure it works? That is exponential and being multiplied. Is that always between 0 and 1? F of 0 is a. I'd have to think about it for a second. F of 0 is a, f of 1 is b, and it is continuous. Yeah, okay. Yeah, it's exponential, so yeah, that works. That's interesting. Yeah, it's definitely not the one I had in mind, but yeah, that does work. I just had to think about it for a second. Yeah, so we see a couple of things. So f of x is a times b. I'm special, indeed. Or yeah, this. There are a couple of ways you can think about this one too. Whereas that, yeah, a times 1 over, yeah, a times 1 minus x plus bx. So the reason I tend toward this is like we're not going to talk much about homotopy in this class, but in terms of like this notion of continuous deformation, which I'll also talk about a little bit later when we talk about the cylinder kind of being homeomorphic to the annulus. This is what's called the straight line homotopy. It's very useful, like in a lot of areas. It's something that shows up a lot. And basically what you're doing, right, is just you've got this interval and you're just parametrizing, right? You're just taking it to something else. It's some different length. And so you're just saying, like, where would I be at time t? So you start here, and so you're mapping this to this to this, and then it's all, linear. I'm bad at drawing. These ones should not be vertical. Right. So you just kind of fan out, if you will. So it's pretty interesting. What if a equals 0? B over A. Oh, yeah, that does seem like a problem. Yeah, it shows up fine for me, Devin, so I haven't had an issue. Discord pictures, Bob Ross. That's just because I'm very interesting. It has nothing to do with drawing. Yeah, so A equals 0 is a problem here, right? But otherwise, yes, this would work in general. But yeah, I think the straight line is a really useful one that, like, I mean, it is in the book on buildings that, like, Mark and I used for 90% of our thesis. Straight line homotopy shows up a lot. I don't know if you read that part, Mark, as much, but that was in, like, the Z realization and, like, cat zero spaces. But anyway, it's important. So this is a good one to know. So this has a name. It's the straight line homotopy. And this is very common in general if you're trying to, like, contract down or, yeah, expand out. It's just kind of to send things along on this straight line. But cool. So yeah, all these things are homeomorphic, and so basically any kind of open interval thing we can view as the same for us, right? Because we have this notion. We talked last time about how being homeomorphic is an equivalence relation. Any thoughts on b minus ax plus a? That is indeed the same thing. What's your inverse here, by the way? Right, so this is not necessarily one with an obvious inverse. Like the other ones, it was very obvious, right? It's like you do x minus a, you do minus x back, we have e to the x, we have ln of x is your inverse. Like these are very obvious continuous inverses. What's our inverse here? B minus, oh boy. B minus b plus b, yeah, it does. Well, yeah. Yeah, it should be a linear equation. What is this equation? So this is one where you can just, like, do your switch x and y and so. Okay. I think it's the other way around. Because you want to be within, yeah. Yeah. Yep, awesome. And again, this is a constant in the bottom, and so this is very clearly continuous. Cool. Okay. So, 210 is, that's something probably better left for another time. For time purposes, and also we're not going to use it a whole bunch, but that might be another like scaffolded problem. I think I'm basically ready for the next problem set now. So yeah, wanted to talk about 211, and then I think everything from here on is pretty useful in getting used to constructing these homeomorphisms. So here, right, we have a function. So we'll have some more ways to show this is not homeomorphic later, but right now we don't have the tools yet. We haven't proven these things. So for instance, like compactness. I think all of them are clearly bijective if you know they have an inverse, right? Yeah. Yeah. Yeah, I mean, that's why the first ones, the inverse is more obvious, but yeah, like with natural log and e to the x, like we know these are literally inverse functions, and so yeah, we know they're bijective. Because I've specified them, okay. Yeah, you're specifying the domain exactly to be that way. You cut out. All right. Yeah, there's noise. Yeah, I mean you're specifying them basically so that they're exactly like onto, right? Like so 0 to infinity is exactly where the natural log is defined. If you tried like r to r, that doesn't make sense. And same with like e to the x, right? If you did that back from r to r, you would only get 0 to infinity, but we like define it so exactly so that it is going to be bijective. And I think with things that are so familiar from calculus and knowing their domains and ranges so well, like it's also okay for like the basic things to say like by inspection. Yeah. Okay. So basically, yeah. So later we'll see that like this guy's compact, this guy is not compact, and like if you have a homeomorphism, then well it would preserve that. And so we don't have that tool. So here we would just kind of say, okay, well we're given this specific map. Why is this not a homeomorphism? Because f is, as you had to show, right, it's bijective and continuous. So, I mean, the bijection, you can either construct an inverse or, and by the way, so like the inverse ensures it on the domain. Like, so what it means to be an inverse, right, is that f composed with f inverse here, so this would be equal to the identity on S1. And then f inverse composed f would be the identity on 0 to 1. And so like this would mean it's bijective. So like if this works, then you're good. And like if you started with the wrong domain, if you were like too big, if you started from like R, for instance, like this wouldn't work. You wouldn't get the identity back because you would go from like all of R to just the interval from 0 to 1. And then that's going to be surjective, but not 1 to 1. And so it's like not the identity when you compose. So like this does take care of it. Like this is the definition that like makes it a bijection. That's the equivalence. So here, I mean, I think you can either show directly it's 1 to 1 and onto, or the inverse function's pretty easy because like a general point on the circle looks like, say, cosine of t sine t, right? Where t is between 0 and 2 pi, and I'll do strictly there, right, because I don't want to double count or anything. And then where does this go? Well, it's just going to go to t over 2 pi, right, because I just want to make it fit into 0 to 1. And it's pretty easy to check these. I mean, you can do it kind of by inspection, right? So like if you do f inverse first, you go to t over 2 pi, and then you do f, well, you multiply that back by 2 pi, and so you get cosine of t sine t back. And then f, you get this guy, and then you divide them by 2 pi, so you get cosine of x sine x, and then you go back, f of x is, you multiply, then you divide it, and so you get back what you started. You go to 2 pi x, then you divide 2 pi x by 2 pi to get x. So it's bijective. Why is it continuous? What's the easy argument that this is continuous, given things we've proven in class? Yeah, so the coordinate functions are continuous. And so the two things that make it up are continuous, so it's also going to be continuous. Cool. And so the failure, right, f inverse is not continuous, but only on 0 to 1. Why do you say that? Yeah, it's continuous on R, so it's going to be like right continuous there at 0. I'm not sure which map you're talking about now. It's like infinite things for the inverse. What do you mean by infinite things? So remember that, so what I'm afraid of there is realize that we're only going between 0 and 2 pi because x is between 0 and 1. Should prove separately that it's continuous at 0 using 191. What is 191? Oh, you mean like the specific point? No, I mean, it's still like the preimage of any open set in the circle is going to be an open set in 0 to 1. Right, we've looked at open sets in the circle before, so do you have headphones? Right, so like if you take an arc on the circle, then this is going to give you, again, if it contains, right, if it contains this point, then it would be like this union this inside 0, 1, and then otherwise it's just itself, right? So this guy would just go back to some open interval. So in either case, you get the preimage of opens are open. So it is continuous everywhere there. So what Rippy's saying here, so we've got infinite things like 0 spits out all multiples of 2 pi. No, so we are restricting ourselves in terms of where we're going, right? So like we're not mapping back to all of R. Like we do restrict to mapping back to 0 to 1. Right, because like 0, we fix this. We're not looping all of the circle and double counting points. We just want one copy of the circle, and then we map that back. Yeah. Right, like that issue, your map would not be well defined, right? The t over 2 pi would not be well defined because, you know, equal points on the circle would map to different things, and so that would be bad. Because of this. Because the preimage of any open arc on your circle, any open set, right? So those are your basic open sets. So preimage of any basic open on S1 is still open in the interval from 0 to 1. Okay. So, I mean, you're not completely wrong in terms of where you're looking, Rippy. So, I mean, the issue should definitely be, right, like, I mean, it seems like everything is okay except for here, right? Like, this seems to be the problem. So, I think you can think about it one of two ways. So, maybe you had never heard of open sets before, and instead you're just thinking like the epsilon delta kind of thing. F inverse is? No. F is continuous, but to find F being continuous, you look at its preimages. So if I'm coming in, right, so F inverse is sending me from my point to, or basically my angle, to that angle over 2 pi, right? And so if you look at like points in this little area versus points in this little area, right, they're close together, but their images under F inverse are very far apart. Right? Because these guys in red map to things near 0. They map to things near 0, where the things in blue map to things near 1. And so you have things that are near each other that map to opposite ends of this interval. So like that's the issue, and you could pretty easily, well, I mean, you could definitely construct like an argument with epsilon delta there. But did anyone find like an open set that does not map under the preimage to an open set? So remember, the preimage here would just be F, right? So you'd be looking for some U that is open in 0, 1 such that F of U is not open in S1. Yeah, I mean, it is kind of... yeah, I mean, there's like a jump as you go across the 0.10 on the circle. Yeah, kind of. Because there it's like simultaneously 0 and 1 in a way. Not literally, because we're not mapping to the closed 1. Could you just say 0 to 1/2? Is it? Yeah, exactly. So basically, it doesn't have to be 0 to 1/2, but something that starts at the 0.10 on the circle and ends somewhere before that, but is open, right? Because F of 0 to 1/2 is exactly the semicircle, like the top half, but not including this end, but including this end, and this is not open in S1 with the subspace topology because you cannot intersect either, you know, open balls, open boxes, whatever you care about more, and include this endpoint. Okay. So this would be why F inverse is not continuous. Does that make sense? Yeah, those are equivalent. Yeah. You're citing 203. Yeah. Oh, I understand. No, yeah. All you're saying is that F is not a homeomorphism. Right? That was the problem. I mean, they are, in general, with these topologies, not homeomorphic. Yeah. Yeah, so we can prove something more general later when we have more tools. Haven't we? Oh, right. Yeah. The point of the problem is just to show F is not. Right, like read 211. It's just that F is not a homeomorphism. But it's true that they're not homeomorphic in general. We don't have the tools yet. Okay. So 212, I think it's important to get the picture first, right? So we've got the cylinder. It's S1 cross 0, 1, right? So I'm thinking, got this cylinder guy. And basically, I've got my circle. This is my 0. This is my 1, right? So I'm just scanning my circle up this interval of length 1. And then I've got my annulus. I'll call it A because I called it A in the thing. I didn't realize that. And here, right, we just want, 1 is between x squared plus y squared is less than 2. Right, so basically we've got the unit circle, and then we've got radius 2, and then you have all of these points here. And, right, the outside of the cylinder is included, but, like, there's no interior to it. There's no thickness to it. So if you remember that straight line homotopy thing I was talking about, I think that's a useful way to think here as well. So what you're really doing is, I view this 0, 1 thing as like a time parameter. And so what I'm doing is I'm just like deforming my cylinder into this annulus over, 1 unit's length of time. And so how? Well, I mean, this is the unit circle, right? My base at 0. So I'm basically viewing this as, okay, that's the interior of this annulus, the inner circle. And then my top, well, somehow I have to like stretch this out so that my top matches with my outside, right? And so what I'm doing is basically just extending my circle, right? I'm expanding it over time to get out. And so the way I view this is kind of like unfolding. You're like unfolding the cylinder. So as you go up, you're just kind of like slowly pulling it down because your base was already here, right, on the inside. And then you just kind of, as you slowly bring it down, by the time the whole cylinder is on the table, it looks like the annulus. Does that make sense, like pictorially? I look at it as ripping away and stretching rings. What do you mean by ripping away? The word rip terrifies me because, like, we're not allowed to glue or tear. But I think you just mean pulling, right? Like, it's just stretching, not literally ripping. Okay, yeah. Yeah, I agree. I understand. Yeah, I mean, that is basically what we're doing, right? I mean, as you go up, like, each cross-section is exactly, a circle, and you've, like, stretched it a little bit when it comes down. Okay. So, we've got the picture. Seems like this is true. So can we come up with actual functions? We just stretch and smash it. Yeah, kind of. It's a coffee cup. It's not a coffee cup. This is not the torus. You'd have to glue the top to the bottom to do that, right? Yeah, exactly, yeah. The coffee would fall out. So here, I think I gave the hint to think of these points. You can either think of it like truly in polar coordinates, or like I just did, again, like kind of the cosine t, sine t, r. I probably should have said, since this is a time parameter, that's t, but I was just thinking a little bit in terms of polar. And so what is this mapping to? So like when r is 0, I should be mapping to the unit circle itself, right? And then at the end, I want to be mapping to, well, the thing of length 2 would be like 2 cosine t, 2 sine t, right? This would be the outer circle. So like, how do we get there? What's our map? Not bad. All right, well, I'm getting no responses, and I know I talked with Devin and Jack last night, so screw it. I'm just going in. So you get r plus 1 cosine t, r plus 1 sine. Yeah, Jack. Yeah. Why are you squaring it? The circle of radius r is r cosine t, r sine t. If you square it, then you get x squared plus y squared equals r squared, which is also true. But like the literal distance is r, and that would be like the square root of x squared plus y squared. So this is right. Okay. Yeah, sorry, that was a lot of sound that came out of nowhere. Yeah, that was indeed right. And so if you want to show this is a bijection, again, you could do it one-to-one onto. I think, again, it's probably easier just to do an inverse because it's like pretty clear what you're doing. So if you start with a general point over here on your annulus, right? So you have like some r cosine t, r sine t, where r is between 1 and 2. Well, then you just map back to, again, it's like the same point on the circle, but then it's just you've reduced the radius by 1, right? So it's just cosine t, sine t, r minus 1. And so you can check that it composes, but it should be clear by inspection. So that's a bijection. Why is this continuous? So this is a little weirder because we don't just have like a very, yeah, I mean, again, it's kind of, look at these coordinate functions, right? But the issue, right, is you're not just coming from like R or like a very obvious thing. You're coming from like another product space, so maybe that feels a little bit weird to just say like, oh, it's cosine and sine, so it's like definitely continuous. I mean, that is basically the case, but it's not like immediate in the same way. And then another way to think about it is like, what are preimages of open sets, right? So like, if I call this F, well, again, I think it suffices to really look at 1, right? Because F by 203, this is true if and only if U is open, if and only if F of U is open, right? So if I take an open set over here, what does that look like? Well, open sets in S1, again, it suffices to look at basic open sets because F of a union is the union of, or the image of a union is the union of the images. So you're thinking basic opens. Yeah, it'd be like a rectangular patch. Exactly. So U is like a rectangular patch. And then this means that f of U yeah, it depends on how analytical you want it to get. I don't think it's necessary to do that or necessarily beneficial. I mean, we can look a little bit at that with like the next problem, but yeah, I just usually you won't do that, but like you could if you really wanted to. I think it depends. You still have to find the map and you still have to understand like what's going on. Well, I mean, you have to remember that these are also like fairly simple spaces. You're not always going to be able to just draw the picture. But like things inside R that are like pretty easy to draw and describe, and we know what the open sets look like. Yeah, it's not too hard to like avoid that last little few percent of rigor and still convince someone that it's true. Right, like basically what Mark said. True, this homework was hard and probably unnecessarily. I mean, I suggested to look at the picture and to use things you know from calculus for that reason. But yeah, like what Mark said is very true. Like it's as long as you're not convincing yourself of things that are false, then it's easy. But that is definitely something that can happen. So if you have a rectangular patch here, right, it's basically just going to map to like a patch inside the annulus the same way, right? And so, yeah, this again, is this the most rigorous? No, but I think we know enough from talking about the product topology that like these are what the open sets will look like. We can see because we know how these maps work, what's going to happen, and so like we can convince ourselves that this is true. And again, like for some of these, like that really will suffice to look at these open sets and talk about like what they look like as opposed to like the most analytical description. Okay. So the next one was probably hard. Wait, this is yeah. This is the disk one, right? So, right, D is our unit disk, and what I call it, S is -1 to 1 cross -1 to 1. Wait, we're done? Yeah. Again, depending on how much extreme rigor you want to show. I don't think it's really beneficial to get like super into the weeds and talk about, okay, so like you assume you have an open interval here and an open interval here, and what that looks like is you're mapping these, like it's essentially you will get this picture. And so like by 203 that would be enough. Like I am okay with that. I mean, I know you're joking, but like it wouldn't be from first principles, right? I mean, it would just be like demanding 100% rigor, which is fair. And in a lot of cases, we do that. But like, there is a point in topology where usually people will hand wave these things because it is clear what's happening, and because like these are nice maps that we know a lot about, Like we're doing cosine, we're doing simple like scaling. Yeah. Yeah. Details indeed are for analysts. That's why we didn't do all the epsilon delta, right? We just talked about open sets, and life is easier that way. Okay, so here we've got this guy versus this guy. Didn't believe it. It's true until someone argues. I mean, it's not completely false. So why are these homeomorphic? So I mean, you can kind of see what the map should be doing, right? We're like stretching out our circle to kind of match the edges of the square. But can we like define some kind of map, or can you tell me like why one point goes to one point? That's the real issue. Like, even if you can just describe that, like what point, so if I give you some random point here, tell me where it maps in the square, then like I would be pretty happy. You can define a map here, and I'll do it, but yeah. Yeah, okay, so this we'll say has radius r, then you'd be going from like okay. The quadrants stay with themselves, right? Yeah, they do. By 209, edge maps to edge. What do you mean? But what's your interval in the disk? In the disk? Oh, you're saying like take horizontal cross sections going up? Maybe. I hadn't thought about that. I think that would be challenging. I think that would be more challenging. I'm not sure that makes a lot of sense. I don't think that's going to be continuous. Because you're like filling stuff out. Yeah, that seems like an issue. Yeah. Right, exactly. Yeah. Kinda, yeah. So it is somewhat polar coordinates is, yeah, what I was kind of thinking too. So, right, you take some point r theta over here, then what you're doing is you're looking for the same point over here on this box of, I guess, side length 2r, right? So you're looking for like the same angle. So like very rigorously, I guess, what I was thinking about was like D is the union I'm not sure exactly what you mean. I think that's what we're doing, if I interpreted you correctly. Yeah. Yeah, I mean, that's what we're doing. That is this map. That is this map. Yeah, the issue, right, is like they're not equidistant. So like what you're really doing is like array at angle theta intersects dr and sr at exactly 1 point. Those are the points that get matched. Right, so you just take these like interior circles that build out to your whole circle. You take these interior squares that build out to the whole square, and each ray, if you give an angle, will intersect at exactly 1 point. Map those points to each other. So if you want to see like an explicit map, so for SR, by the way, right, so how do we do the square up here? Well, it's really that like the max of the absolute value of one of the coordinates has to be 1. And in general, that's going to be the case. So this would be x, y such that the max of these is equal to r. Right, because then you have like either, if x is r or negative r, you get those little horizontal patches, and then y equals, wow, I did it the other way around. X, y is negative r or r, then you get like the top and bottom of your square. And so if you want to map some x, y in here to dr, well, how do you get a point on the unit circle, right? You would divide by the length to make it length 1, right? So you divide by the square root of x squared plus y squared. Well, how do you make sure it's on the circle of radius r? Well, then you just multiply each coordinate by r. So this would go to rx over the square root of x squared plus y squared, ry over the square root of x squared plus y squared. Because basically, right, you're just like dividing by the distance to make it unit, and then multiplying by r to get it on the right piece. And you can check that these coordinates, if you call this x prime and this y prime, then x prime squared plus y prime squared, well, you're going to get r squared x squared plus r squared y squared over x squared plus y squared. Well, that's exactly r squared. And so this does indeed lie in dr. And then your inverse map is pretty similar, right? If we divided by this here, our inverse should be multiplying by it. And then we need to divide by r, but like it's not exactly r here, but instead you would divide by the max of these things. So your inverse, so this would be SR to dr. Your inverse from dr to SR is that xy goes to x times the square root of x squared plus y squared over the max of these two guys, and y times that over the max. Whatever, max. And these are inverse to one another, so it's a bijection. It's continuous because, I should be careful on this bottom one, right? So here, and 0, 0 goes to 0, 0. So this is for x, y not equal to 0, 0. Right, because if the max of my x and y is 0, then I have a problem. So I can't map it with that map. So, I mean, you'd have to check continuity there at that point that it really goes to that. So you'd probably have to do some limit business. But, I mean, it's going to be true, right? Like as x and y both get super, super small, this is going to go to 0, 0. And so these would be your explicit maps, and this is generalizable. So like the next problem, which I didn't assign and won't assign, was to do this with like the cube and the sphere, or I guess the closed ball and the closed cube. And yeah, this is why you often skip details, indeed. And so in that case, you do the same thing, except for instead of this, you have square root of x squared plus y squared plus z squared. And down here, right, it's the max of x, y, and z, and the square root of x squared plus y squared and z squared. And then you just have one more coordinate. But like this is generalizable even to Rn, so you can do like the in ball and like the in cube. Okay. Which is cool. Thoughts? Questions? Okay. Yeah, it is pretty cool. And I think you guys had like the right picture, right? It's just like this is why, like, if I write this paragraph, any topologist is going to be like, "Yep, you nailed it," because you're really just doing like the straight line homotopy on each of these little pieces, right? You're just kind of saying like, "Oh, okay, like it wasn't quite there, but it intersects at one point. I just have to stretch out this line a little bit and make it work." And then you see like how to define the maps. It's like you can do it, but it's nasty. And like checking continuity of this second guy, that's going to be nasty. It's doable. It's just that, is that time well spent, right? Okay, so now we're ready for quotient stuff. So I want to talk about this example, I guess, and then we may not finish it this time, but I will prove 217 and 218. They're very crucial. They are what we use, and the idea behind those is essentially this is the universal property of quotient groups or of quotient spaces, and in general, I guess the universal property of the quotient. So you would get the same result in group theory about quotient groups. Analogous. You're not talking about topological spaces there, but like replace the map with like a group homomorphism, replace the quotient space with the quotient group, and suddenly you have like the same thing. Right, replace homeomorphism with isomorphism. So this is actually a very generalizable thing, and I think it's useful to try to go through one argument first and see why it sucks, and then talk about the universal property and why it's better. Because this is where having some heavy machinery can be very nice and avoid dealing with these like really minor details that can be really troublesome at times. So our map here is we want to go from this to this, and the idea, right, is R2, I guess I can just define tilde, right? So again, this was xy is equivalent to a b if and only if y equals b. So they're equivalent if and only if they have the same y coordinate. So what did you think of as a map? So I have a general equivalence class. Where should this go? No. Our equivalence classes are on the ordered pairs. No, it's not the same thing. Yes. Yeah. Yeah, it's definitely a different thing. So where should this go? Okay. Yeah. Yeah. And so like what you just said is basically what we have to check. So we have to check that this map is well defined, right? You may remember this from quotient groups, right? We had to talk about well-definedness because the map has to make sense no matter which representative I choose. And so that is basically what Nick was saying is like AB is going to be equivalent to like 0B, and so you can just view this as like the vertical line x equals 0. But we have to check this, right? So like if x is equivalent to y, or sorry, if xy is equivalent to AB, we have to check that they get mapped to the same thing. Oh boy. Brackets on brackets, all right. And this is true, right? Because this one would go to y. No, it's exactly the opposite. So this is saying if you have two things in your domain that are equal, then they go to equal things. The other one would be if two things go to equal things in your codomain, then they were equal to begin. So it's the other direction. Right. And basically the one-to-oneness here follows because this is actually an if and only if statement, right? So I really don't need to even say if here. So this is equal to this if and only if y equals b, if and only if xy is equivalent to ab. And so the direction from bottom to top gives me well-defined. And top to bottom gives me one-to-one. And so equivalence relations being these if and only if statements about what it means to be equivalent, basically we'll get, if it is well-defined, it's going to be one-to-one. Thanks, Mark. Okay, so basically we're a little bit on our way, right? So we have a well-defined map, it's one-to-one. So then we would have to show that it's surjective. That's pretty clear, right? I mean, we're just mapping to the y-coordinate. We can have any y-coordinate, so this is clear. And then the last one would be, why is f actually a homeomorphism? And this is where it's hard. So this is why having these other notions is nice, because what are open sets in, right? So like a natural way you might think of this is, again, 203. So like U is open in R2 mod tilde if and only if f of U is open in R. But that seems tough, because like what are my open sets over here, right? They're inside this space of equivalence classes. What are the open sets? Do we know? So remember, this is a quotient space. Kinda, yeah. So it sounds like you're pushing it forward rather than going back, which is my only concern, but it's roughly the right idea. So because P is a quotient map, right? So P is the map from R2 to R2 mod tilde. Then by definition of quotient map, U is open if and only if P inverse of U is open in R2. So I think what you were doing is basically starting on the right side, but it wasn't necessarily a preimage. Basically, you will never be able to get a preimage that is an open rectangle. You can only get these open, like, bands, I guess, like infinite bands, right? So like in R2, your preimages look something like this, where you have everything in here, right? Because the preimage of a single set, right? So like preimage of just this guy, say, is exactly the line y equals b. And so if you have a preimage which is open, it's going to be some union of open bands. The quotient map is continuous. The quotient map is always continuous by definition. Yeah. That's how we define the quotient topology. Right? Like the quotient map is, like, to be a quotient map, it's exactly this. It's surjective, and that the open sets in your quotient space are open if and only if their preimages are open. So these are like what my P inverse of U looks like, right? Looks like this. And so this is open, right? So if it's open, looks like this if and only if U is like an open interval's worth of equivalence classes. So what I mean by that is basically you're allowed open intervals of, so basically like U, then you could write as, if it was a basic open, you could say it's the equivalence classes of, say, yeah, no, I can do that, 0b, or I'll say 0y, such that y is between a and b, but it's an open interval. Something like this. And then think about where this maps, right? So then f of u, well, that's just going to be AB, and that's open in R. So basically, what you do is you travel up first, right? Because the only way to define an open set in your quotient is to look above. And then you look above and you see these bands, and you're like, okay, well, what does my projection map do? Well, it just shoves these all to the, y-axis if I want, and basically I'm just getting a union of open intervals in R. And so like the point here is, we had to go up through the top space anyway. Is it just faster if we only look at that and don't worry about the quotient? And the answer is yes. Okay, so that's this theorem 217. It basically says it suffices, 217 and 218, you kind of have to get both. But it basically tells you that to check that that this map is a homeomorphism, it suffices to look at properties of the map from the top space, say R2 here, to R in this case, or the one you're going to. Not just for continuity, for everything, for the homeomorphism entirely. So that's 218, kind of follows from 217. So both of those together. Same cardinality? Yes. If that's what you mean. They are not, however, going to be, yeah, all right. But like that's not really what we're showing here. We don't need like a bijection between the two. Because we only need a bijection between the quotient, not the whole space. That's not going to be true here. Because this is clearly, right, this is a projection map from R2 itself, and that's definitely not a bijection. Yeah, let's talk about it. So there are many different kinds of uncountably infinite, but in this case, yes, R and R2 actually do have the same uncountable cardinality. That was kind of what was getting talked about on Discord a little bit last night. Basically, you can look at decimal expansions because R is equivalent to 0, 1, and basically you can like interleave the two. So like if you have two decimal things, you just take like first decimal of the first, then the first decimal of the second, second decimal of the first, second decimal of the second, and then you get one decimal. So that would be your map. Okay, so 217 I think is best used with like a diagram. All right, so basically we have x, it goes down to some x mod tilde, and then we're going over to z. And so this is just your quotient map. This has the quotient topology on it, the quotient space. And so what we want is basically if we have a G, so let me make sure I state it exactly how I did in here just to be consistent. Yeah, so if G from X to Z is constant, so constant on equivalence classes, this is of X, so basically what this means, right, is that G of X equals G of Y if X equals Y. So this just ensures basically that your map is going to be well defined out of the quotient. Yeah, because we want this triangle to commute. Basically, we want G to be equal to F composed P. And so if you do P first, then you do F, and this is supposed to be like defined in terms of G, right? Then like the same equivalence classes have to go to the same point for F to make sense. And so we need G to be sending things in the same equivalence class also to the same thing, just for this to actually work. So that's what this means, that it's constant on, I mean, I wrote like pre-images of these things, but that's exactly what this means. And so, yeah, so then we get then G induces, so that word shows up again. Basically, that F is just coming from G, a map F from X mod tilde to Z such that G is F composed P. And I mean, it's literally the map that you think, right? So like we have a map G from X to Z. So where does F of this equivalence class go? It just goes to G of X. And this is well defined exactly because we made sure of it with this underlined thing. And then the result we get, and this is just the first part, so I mean 218 is what talks about the actual homeomorphism, and we'll prove this next time because it's worth talking about. It's important to understand this diagram. So F is continuous if and only if G is, and F is a quotient map. Wow, quotient map. If and only if G is a quotient map. And again, quotient map means surjective and that preimages, so, and U open in Z if and only if F inverse of U is open in X mod tilde. So that's what it means to be quotient. So essentially, if you just have this map, right, so basically I'm reducing all my work to just checking out G. It is, yes. Yeah, continuous would be just one direction. The forward direction there. So, right, like we've reduced it to like, okay, I don't have to deal with equivalence classes. I don't have to worry about that in this weird quotient space. I just look up top, and I turn my pen on. I just look up top. I check out this map G. If it is the same on equivalence classes, and it's continuous, then I know that this map is continuous for free. If it's a quotient map, then this map is a quotient map for free. And it turns out in 218, we'll see like it's just a little bit more work. If G is a quotient map, then F is actually going to be a homeomorphism. And this should remind you of the first isomorphism theorem from group theory. If you had a surjective group homomorphism, then G mod the kernel was isomorphic to the image. Well, if you start with a surjective map, right, then this is going to, or sorry, phi of G, G's. And so in this case, this is equal to H. And so basically you're getting Z as some quotient of G. And that's exactly this diagram, right? G, this would be like H, and this would be the quotient of G by the kernel. So it's exactly the same thing. And again, like this is a universal property. This is true for like any kind of quotient thing. So it's really like all these proofs are very, very similar, and it basically is just like the same diagram tells you the same stuff just in different contexts. Alrighty, well, we are out of time. I mean, technically I would say like the quotient object, but I mean object probably sounds a lot like thing unless you're really thinking about a category theory. So yeah, quotient thing. Okay, so I don't think I'll ask you to prove this. Yes. I won't ask you to prove 217 and 218. I'll do that next time, but I do want you to try to think about how they're relevant. So looking back at 215 and what we did, can we find a much quicker argument using this theorem than trying to like go through the equivalence classes and like drawing the weird picture and trying to think above? Can we just like go from up top and make our lives easier? And it should seem easier because like what's the map from R2 to R there? It's literally just the projection, which we know to be continuous, open, surjective, and stuff. So like that should be like 2 steps compared to the work we did before we knew this. So that's why it's cool. Alrighty. Any questions before I depart? What the heck is that emote? Yes, but not now. Fair enough. Yeah, I expect this stuff to be a little bit confusing. Quotient spaces are a little bit tough, and like the universal property stuff it's super useful, but until you start putting it to use, I think it's it seems weird, or maybe like, yeah, a bit esoteric. Do you know of any topology textbooks / online resources? Yes. I mean, we have plenty of examples in here, but like, I guess, yeah, I mean, Moncrief's is a very good one. He's probably the most common undergrad textbook that is used. Yeah, Mark agrees. I know Adams and Franzosa is decent, I think. I mean, I think that like what I'm showing you in these proofs is an accurate picture, but that's fair. All right, I feel like we can just talk in Discord, honestly. I'll just cut stream. All right.